how to cope with the variables of the gravitational force exerted on planets with a smaller mass than Earth. If you think about the next trips to return to the Moon or land on Mars, you cannot avoid the consequences deriving from the variation of the gravitational force of these celestial bodies that significantly impact the physique of cosmonauts. These are planets that have different levels of gravity. The Moon, about a sixth of that of Earth, while Mars exerts more or less 38% of that of Earth. Therefore, in these cases, ballast the body to reach a weight comparable to that of Earth could be the quickest and most appropriate solution to be able to maintain the bone solidity of our physique. How to do it is a more complex challenge, since we must take into account the many factors that distinguish the balance of our organism with the surrounding environment. One of the least considered, in my opinion, is the exercise of atmospheric pressure on our entire body surface. It is a problem found on most planets without an atmosphere, not only because of the impossibility of breathing, but also because of the absence of the compressive force that guarantees the balance between the fluids present in the human body and the surrounding environment. Hence the need for pressurized suits and environments to prevent internal body pressure from increasing dangerously, compromising the structural integrity of the physique. What many of us fail to realize is the fact that we are at the bottom of an ocean of air, more or less in the same condition as those marine creatures that live in the abyss, where the internal pressure of their body is able to counteract the extreme values of pressure present at those depths. It follows that the air pressure, equal to 1 kilo and 33 grams per square centimeter, is exerted on the entire surface of our body, which in an environment without an atmosphere would end up triggering the problems mentioned above. If we then accept the assumption that gravity exerts its force vertically on any body that rests on the mass that determines it, we must not overlook the importance of the correct distribution of the ballast, since in our case it would not be desirable to place a good part of the weight on the head and shoulders, elements directly subject to the aforementioned pressure. To give a figurative example of how gravity loads the parts most exposed to its action, it is sufficient to observe the peak of a mountain to note that the snow, with its relative weight, is deposited on all the protrusions that interrupt the verticality of the rocky body. Similarly, to prevent the cosmonaut's ballast from exerting its pressure exclusively on the horizontal and oblique surfaces that oppose the verticality of the remaining surfaces, it will be necessary to act on the pressurization of the suit, so that the weight also affects the areas less subject to the action of gravity, so as to partially and proportionally distribute the added excess weight to ensure the maximum integrity and physical efficiency of the body. Reasoning by absurdity. A person who weighs 80 kilos on Earth, on the Moon, would weigh 13,600 grams. Therefore, to re-establish the same exercise of the Earth's gravitational force, he would have to ballast his body with about 400 kilograms of weight. On Mars, however, he would have to carry 130 to adequately weigh down the 30 kilos and 400 grams of weight that his body would have on that planet. These solutions are essential if we consider the fact that a human being is not structured to live on planets that are not able to reproduce terrestrial environmental conditions. If we think back to the television series Space 1999, which narrated the adventure of a lunar colony that, following a series of terrestrial explosions, had begun to wander in the cosmos, we cannot help but notice the incongruity due to the physical appearance of its guests, who, despite the very low gravitational force of our satellite, they maintained steady movements and a normal physical appearance, when it is established that low gravity heavily compromises the bone structure and muscular efficiency, as well as not allowing steady movements like those we are used to on the Earth's surface. At this point, with the knowledge of a layman, we can try to hypothesize how the covering necessary to ensure the maintenance of our physical balance could be structured. It should be a complex capable of modifying the centers of pressure based on the posture of the body, whether it is in an upright, sitting, or lying position. One of the possible solutions could be to adopt a suit composed of small vesicular meshes, intercommunicating with each other by means of microducts, in which a fluid substance with a high specific weight and a gas suitable for exerting pressure on the surfaces of the body not affected by the momentary force of gravity move separately. The two elements present in the aforementioned vesicles would not come into contact with each other because they are separated by a membrane that allows the gaseous part to exert the necessary pressure in direct contact with the epidermis, while the part containing the ballast fluid would affect the external surface of the coating. As an alternative to the future ballast fluid, lid plates could be used, different in weight and size, displacing them based on their weight on specific areas of the body to produce the correct pressure, even on those spaces not directly affected by the force of gravity, thus promoting the maintenance of bone-muscle balance. These are just hypotheses. How would you solve this problem?